Hello, and welcome to a lecture on section 17.4 about flow lines for a vector field. Up until this point, we've been looking at vector fields from the perspective as maps from points in R2 to vectors. What we want to do in this section is add a context to a vector field. So in the picture down below here, imagine that our vector field is actually a velocity vector field for a river current flowing across some riverbed. And now we think of the vectors in the field as being velocity vectors for the movement of water over some riverbed. So these vectors tell us, for example, over here, this vector here tells me that at this point the current in the river is flowing in the direction given by this vector. So this becomes the velocity vector for the fluid flow at that point, sort of here towards the upper left, and the length of the vector tells me how fast the current is moving at that point. So our vector field then we can think of as a velocity vector field for this fluid flow. And what we're going to be after are called flow lines, and flow lines are paths, but they're not just arbitrary paths, because in this vector field you can see there's two paths, C1 and C2. And the flow line is a path such that if we move along the path, the motion along the path would be what a particle placed at, say, the starting point on the path. So in C1 the path starts here, and C2 the path starts here. Now, not both of these paths are flow lines. Only one of these paths is a flow line. So when you're looking at these paths C1 and C2 and you're asking which is the flow line, what you want to ask yourself is that if the particle were placed in this river, and the boat, if the particle was a boat or a piece of paper, in what path would that boat flow through the river? And you can see quickly that you would eliminate path C1, because certainly if you place a boat at the origin, and this is the direction of flow of the river current, the boat is not going to flow along path C1. So C1 is a path, but not a flow line. But in C2, you can see that this path is the path that the particle would move through this river. And in fact, if you look at every point along the path, if you were to actually find the velocity vector for the motion along the path C2 at that point, the velocity vector at that point, which we can compute from r prime of t, would be exactly the same as the vector from the vector field drawn at that point. So the vector field then is tangent to the path C2, and so one mathematical property of the flow line is that if we look at the path C2, the vectors in the vector field are tangent to the path. That becomes the flow line for your vector field. So a lot of questions come to mind at this point. How can we verify algebraically that this path given by C2, when we have parametric equations for C2, is actually a flow line for the vector field? And then the second question is, given an arbitrary vector field, how can we find a formula or a vector valued function r of t so that r of t satisfies this condition of being a flow line for the vector field? And both of those questions will be answered in this lecture. Okay, so let's move ahead here. So the first thing we can do is, given a vector field, here's a class activity. So minus yx, this is the vector field you saw on the previous page. And then, now there's lots of paths that you can create through the plane. So in this case, our path is given by this, r of t equals t comma t squared. So if it helps, x is equal to t. And the second component is y, so y is equal to t squared. And you can easily eliminate the parameter here and just write y is equal to x squared. So that's the actual curve that we're going to draw. So if we draw the curve represented by these parametric equations, we just have our garden variety parabola. And so what I'd like to do is I'd like to check that this path is a flow line or not a flow line for this vector field. So it really comes down to computing the velocity vector for the path, that's r prime of t, computing the vectors in the field, and then at each t, are these vectors the same or not? So are the vectors in the field tangent to the path or are they not? So let's go ahead and do this, and we'll do this through a table. Okay, so we have a table here. To speed up the computations, we did some of the work for you. So here's r in the first column. And then here's r prime. These are our velocity vectors for our path. As we move along the path, these vectors are tangent to the path, and their length tells us how fast we're moving along the path r of t. So this is path dependent. This depends strictly on the parameterization of r. And then over here, this is the vector field, and we've substituted, you'll notice that, remember, x is equal to t, y is equal to t squared. So if f is going to be minus y comma x, you get minus t squared comma t. So that's how this minus t squared comma t came from. That's minus y, where y is t squared, comma x, where x is equal to t. Now, if this path is a flow line for the vector field, then these velocity vectors r prime should be the same as the vectors in the field. And you can immediately see from the first entry in the table that these are not equal. So down on the bottom, I already know, because it has to hold for all values of t, this. So I can say already, just from that first entry, that r of t is not a flow line for f. This vector field f. So if you can find just one point where the velocity vector is different from the vector in the field, along your path r of t, you're done. So we can, fill up the rest of the table here. With t equals 2, you get 2 comma 4. So that's the point along the path when t equals 2. You can look at the velocity vector at that point along the path. That's given by r prime. With t equals 2, you get 1 comma 4. And then you can evaluate the field at that point, 2, 4, and minus t squared, so you get minus 4 comma 2. So these are not, in fact, none of these are equal, actually, it turns out. When t equals 3, you get 3 comma 9. That's where you are on the path at that point. The velocity vector tangent to the path at that point is 1 comma 6. And then the vector in the field at the point 3 comma 9, that's where you are in the field, with t equals 3 would be minus 9 comma 3. And you can see these guys are not equal to. So this path parameterized by r of t is a path throughout the plane, but the path is not a flow line for this vector field. So again, you might wonder, well, how do you find paths that are flow lines for the vector field? That's a good question. We'll get to that. Okay, so in part B, we wanted to show you a path that is a flow line. Again, we're not sort of telling you how we're coming up with these paths. We're just asking you to verify whether they are or aren't at this point. We'll get back to that question in a little bit of where we came up with this function. But so again, here's r. X is equal to the cosine of t. Y is equal to the sine of t. And if you evaluate f minus y comma x, so there's minus y is sine of t, comma x. And so again, to speed up the computations here, we've got r of t, we've got r prime. This is our velocity vector. This is our vector in the field. And you can see that when t equals 0, these vectors happen to be equal. Now, remember, for this to be a flow line, this has to be true not just for one value of t, but for all t. But I think you can see that for all t, this will be the case, because if you compare r prime of t with f of r of t, you can see that these are the same for all values of t. So in this case, because of the fact just comparing these two, the r prime vector with the f of r of t vector, we can say, because this is going to be true for all t, in this case, r of t is a flow line for the vector field f. So we can see that already. So we can compute a few more of these just for fun. At t equals pi over 2, my position is given by cosine of pi over 2. That's 0 followed by 1. R prime of pi over 2 minus sine of pi over 2, that's minus 1 comma 0. And then we get minus 1 comma 0. These two vector functions are the same. When t equals pi, the cosine of pi is negative 1. Sine of pi is 0. R prime of pi would be 0 comma minus 1. And then this would be 0 comma minus 1. And this is true for all values of t. So in fact, this second flow line, and by the way, if you actually parameterize this, what you'll get is a circle centered at the origin in a counterclockwise orientation. So if I go back to the original vector field here, because this vector field right here is, this f is minus y comma x. This is our vector field. And you can see that path C2 looks like a portion of a circle centered at the origin, counterclockwise orientation, and that's exactly what this path that we just found in part B gives you. So if you actually graph this path given in part B, you'll get a circle that's counterclockwise oriented, centered at the origin. So that's exactly the path that we saw C2 at the opening activity on page 1 of the survival guide. So here's a flow line that is. Here's a flow line. In part A, we saw a path that's not a flow line. In part B, the path is a flow line. So this is how you can tell whether a path is or isn't a flow line for your vector field. So we can formally just sort of state then the condition, mathematical conditions for a path to be a flow line. It's fairly straightforward. So given a vector field, notice we're restricting ourselves to the plane. A flow line then is a path r of t equals x of t, y of t. That's what r is always equal to. Whose velocity vector, remember, that's given by r prime. So if you look at the velocity vector along the path at any point t, when t is equal to any value, you get a point along the path. You compute the velocity vector given by r prime. Compare that with the vector field at that same point. So you've got velocity vector on the left, vector in the field on the right. If these are the same for all values of t, then that path qualifies as a flow for the vector field. So if we think of our vector field as a velocity vector field for river currents, the flow line then would be the path that the boat would travel if you placed it in the vector field. So this is one way of thinking about your flow line. All right. Now finding r of t that satisfies this definition requires that you solve a system of differential equations. And systems of differential equations can be quite difficult. We'll look at a slightly more advanced system of differential equations later in the notes and show you how to solve those. So essentially, this is what you have to solve. It's a system of differential equations. Your solution then, when you solve this, is actually a path. So what you get when you solve this is r of t, which in vector form, so the solutions of the differential equations come in the form of, you get x of t, that's one of the solutions, and y of t is the other solution to the system of differential equations, and that solution gives you your vector valued function, which is your flow line or your path through the vector field. So again, one final picture. Excuse me, I'm demonstrating this idea. So here's a vector field right here. Imagine this is a river, and these vectors are the velocity vectors for current flow. And if we place the boat on the river here, the boat's going to move along the path given by C, this path here. Notice all the vectors in the field are tangent to the path C. And it's more than just being tangent to the path. If we look at the velocity vector, if we compute r prime of t at this point, and we look at this vector like we did it right here, the idea being that this vector here would be exactly the same as the vector in the field. So it's not just that the vector field is tangent to the path. The length of the vectors in the vector field have to be identical to the length of the velocity vectors r prime of t at each point in the path. So what you're saying is that not only are you moving along the path in the direction given by c, but your speed along the path is exactly the same as it would be in the vector field. So in other words, at each point C, at each point along the path C, if you compute r prime of t and you look at the length of that vector, which tells you how fast you're moving along the path parameterized by r of t, that speed has to be identical to the speed of the river at that point. If the movement along the path that you've parameterized C is faster than the vector, so in other words, if you were in a motorboat and the motorboat were propelling the boat along the curve C much faster than the current is flowing, the vectors in the field would still be tangent to the path, but your velocity vectors along your path would be much longer than the vectors in the river because the boat is speeding across the river propelled by the motor. So in that case, if your velocity vectors along your path are larger than the vectors in the field, even if the vectors are tangent, that wouldn't be a flow for the field because remember, the flow along as you move along the path, your speed has to be exactly the speed as suggested by the vectors in the field. In other words, the length of the vectors in the field at each point, in addition to being tangent to the path, have to be the same as your velocity vectors along your path as you move through the field. So there's really two conditions that this system of differential equations is suggesting. Tangency is one, and the other thing is that the length of the vectors in the field is exactly the same as the length of the vectors, the velocity vectors along the path given by r prime of t. Okay, so we'll come back to how to solve the system of differential equations in a little bit. So let's just move on. Okay, so I've got a path r of t. I've got a vector field 1, x. I want to show that this is a flow line. So really what I have to do again is I compute r prime of t. You do that on the left. And that's not too hard to do here. So r of t, and remember the first component's x, the second component's y. So if I differentiate t minus 2, I get 1. If I differentiate 0.5 t squared minus 2t plus 2, I get t minus 2. So there's r prime of t. On the right side, I have to compute f of r of t. Write this in shorthand notation. So I have to substitute for x and y into the vector field f. Now, of course, f, the first component is just 1. The second component of f is x, but x is t minus 2. So 1 comma x is 1 comma t minus 2. And you can see that these are the same for all t values. So indeed, r of t is a flow line for f. So that shows that this path is a flow line for this vector field. And we can actually eliminate the parameter and find exactly what this path is just by working with our parametric equations, x equals t minus 2. And so if I solve for t in this equation, I get t is equal to x plus 2. Erase that. And then I know that y is equal to 1/2 t squared minus 2t plus 2. So with a little bit of algebra, substituting for t here, I can eliminate my parameter, 1/2 x plus 2 quantity squared minus 2 times x plus 2, just replacing t by x plus 2. And so I get 1/2 x squared plus 4x plus 4. Distributing the minus 2, I get negative 2x minus 4 and then plus 2. And if I simplify this down a little bit more, I'm going to get 1/2 x squared plus 2x plus 2 minus 2x, and then negative 4 plus 2 is minus 2. And you can see the 2x's are going to cancel. The 2's are going to cancel. And so therefore y is equal to 1/2 x squared. So the actual curve, this path that's parameterized by r of t, is just a garden variety little parabola centered at the origin, with vertex at the origin, I mean. Sort of your parameterization will take you in this direction, and that's what your flow line looks like for this vector field. Okay, so let's move along here. So here's another example here. We've got a path, t comma t squared. Here's our vector field. And before we actually do this, we actually drew the vector field. So this is your vector field f. C is what r of t is. We did all this in Mathematica. And of course, the direction of motion would be like this. And you can see it's pretty clear that if your vector field is river flow and your boat's sitting on the vector field, say over here, the velocity vector for the motion along the path is going to be straight up in this direction. And the vectors in the field are in this direction. So certainly the boat sitting in the river, if the river is the vector field, the boat in this river is not going to move along the path C. So I can tell just by looking at the picture immediately that this path is definitely not a flow line for this vector field. This is not the way the boat would move in that velocity vector field. So how can I show this? Well, again, we start by computing r prime of t, the velocity vectors for our path. These are independent of the vector field. These are determined by the path itself, and we get well, we get 1 comma 2t. And then on the right, if we look at f of r of t, you're going to get x plus y, so you get t plus t squared. X is t, y is t squared, and then x minus y, t minus t squared. And to show that this is not a flow line, you just have to find one value of t. So let's just put, for simplicity, t equals 0. And then you can see that r prime of 0 is equal to 1 comma 0. And that's not going to equal, evaluate f at f of r of t when t equals 0. You're going to get when t equals 0 on f, we get what? We get 0, 0, which is equal to f of r of 0. And so you can see that because the velocity vector when t equals 0 is not equal to the vector in the field when t equals 0, which is just the 0 vector, this path is not a flow for this vector field f. So we've shown that. So let me just say down here, r of t is not a flow line for the vector field f. So if you can find just one value of t for which r prime of t does not equal f of r of t, then the path is not a flow line, just a single t value. So it's a pretty strong condition to be a flow line. You have to have r prime of t equal to f of r of t for all values of t. So that's a fairly strong condition to satisfy. Okay, let's move on here. Okay, so just sort of working with this vector field x plus y, x minus y. By the end of the notes, we'll actually figure out the solution, the paths that actually do qualify as flow lines for this vector fields, and you'll see a little bit of a preview of what's in a differential equations course when we do this. So eventually we'll actually solve the system of differential equations associated with this vector field to have a flow line. So that's coming up, but for the moment, the question is which one of these is a flow line. So in each case, what you want to do is remember the first component is x, the second component is y. When you compute r prime of t, I'll do one or two of these and leave some of these to you. So taking derivatives, derivatives of sine is cosine of t. Derivative of cosine is minus sine of t. Turning to f, f of r of t. X plus y, x is sine, y is cosine, would be sine of t plus cosine t. X minus y would be sine of t minus cosine t. And if you compare f of r of t with r prime of t, you can see that these are not equal for all t. So this is definitely not a flow line for that vector field. Part B. So do one more of these, and then the rest of these I'll leave to you to compute all the derivatives and simplify. It's the same thing in each case. Compute r prime, compute f of r of t. So in this case, x is e to the t, y is e to the minus t. For r prime of t, you take derivatives. Derivative of e to the t is e to the t. Derivative of e to the minus t is minus e to the minus t. That's r prime of t. Turning to f, f of r of t. So substitute x equals e to the t, y equals e to the minus t into f, and so what do you get? You get x plus y, e to the t, plus e to the minus t, x minus y, e to the t, minus e to the minus t. And you can see, like, for example, if you let t equal 0, r prime of 0, the first component would be 1. In f of r of 0, the first component would be 2. So this will not satisfy the condition of being a flow line for f. R prime of t does not equal to f of r of t for all values of t. So just sort of working along this same path and simplifying, you can quickly determine that C, well, maybe not quickly, but you'll determine C is not, and in fact, the only one that does work is D. When you compute r prime of t and simplify, and then you evaluate f of r of t and simplify carefully, you'll see that these are equal to each other for all t. So this part D is actually your flow line for this vector field. But I'll leave those details to you. Okay, so what we want to do in this section is actually take you through the method by which you can actually solve this system of differential equations that you see here. And so you're going to learn a little bit about solving differential equations here. The goal here is not to give you a full course in differential equations. It's just to actually show you how you can find these flow lines given this system of differential equations as a starting point. So we'll do this together. Okay, so here's an optional activity. So here's that vector field we've been working with for a while now. So what I want to do is actually find the flow lines analytically. So turning to the system of differential equations, x prime on the left, f1 of x of t, r of t. Well, we don't know what those are, so all I can write this is x of t plus y of t. That's what the first component of f is, so that's going to be x prime will be compared with the first component, y prime will be compared with the second component. And then y prime of t will be x of t minus y of t. Now, what we're going to talk about here is useful whenever you want to solve differential equations that have this general form, x prime is equal to a times x of t plus some other constant b times y of t. So the differential equation has to have this, or the system has to have this general form for what we're going to show you here to work. But lots of systems have this form, so this is useful. Some constant times x of t. Whoops. Don't know what happened there. plus some other constant. So your expressions are linear in x and y. D times y of t. So this system that we've written here has this general form. And to make matters easier here, just so I can refer to these, I'm going to call this equation 1 and this equation 2. Now the first thing you need to do is you need to eliminate, what I'm going to set up is I'm going to basically turn this system into a single differential equation involving just x. It's going to be a second order, which means it'll involve the second derivative of f, but I'm going to eliminate y from the differential equation. So the differential equation will only involve the function x. So how do you do that? Okay, well, number one, I'm going to differentiate equation 1 with respect to t. Okay, so what would that look like? It would look like this. X double prime of t is equal to x prime of t plus y prime of t. Okay. So that's my first step. My second step is I'm going to actually solve for y prime of t well, I've actually done that. Let me just say, not solve, I really want to substitute. Let me just fix this. So what I'm going to do here is, just so you know, in equation 2 we have y prime in terms of x and y. So I'm going to replace that here. So I'm going to substitute for y prime of t from equation 2 in this equation right here, okay? So what I'm going to get here is x double prime of t is equal to x prime of t plus, and y prime of t is just equal to x of t minus y of t. And then number 3, I'm going to solve equation 1 for y of t and sub here. So what that's going to give me is x double prime of t is equal to x prime of t plus x of t. That's this guy here. Now y of t, if you look at equation 1 and you come over here and you solve, what you get is that y of t is equal to x prime of t minus x of t. So if I replace y of t here with that, what I'm going to get here is minus x prime of t minus x of t. And if I simplify this with goes that pen again. What I'm going to get here is x double prime of t is equal to, now you can see the x prime and the x prime are going to cancel, so those two are going to drop. And you're going to have x and then minus minus x, so you're going to get 2x of t. And for reasons that will become clear in a moment, I'm going to rewrite it. This is x double prime of t minus 2x of t equals 0. So keep that handy. We're going to use that in a moment. Okay. So now let me just say what we have so far. So what we have here is x double prime of t minus 2x of t equals 0. Now this differential equation here is called a linear second-order differential equation with constant coefficients. And methods for solving this are covered in detail in a course in differential equations, but we'll give you a quick sort of introduction on how to do this, and then without all the details, but most of the details. And then if you're interested on the full story, take Math 2A here at Foothill. So let me just skip over this for a moment. Okay, so what I've done is I started with a system of two linear differential equations in x and y. And I reduced the system to something of this form. In fact, my equations is written in this generic form. It's 1 times x double prime of t plus 0, since x prime doesn't appear in the equation, minus 2, try that again, minus 2x of t equals 0. So that's the form of the differential equation we just left a second ago, a couple pages back. It has this general form here. And so to solve this differential equation, what you first do is you assume that the solution, because of the form of the differential equation, has the general form x of t equals e to the lambda t. And you compute x prime under that assumption and x double prime. And then you substitute into this equation 1. And so you get a times x double prime of t is a lambda squared e to the lambda t. B times x prime of t is just b times lambda e to the lambda t. And then you have c times x of t is c times e to the lambda t. That has to equal 0. Factor out e to the lambda t, and you get e to the lambda t times a lambda squared plus b lambda plus c equals 0. And since e to the lambda t is always positive, the only way that this product can be equal to 0 is for a lambda squared plus b times lambda plus c equals 0. And this last equation is called the characteristic equation, and its solutions via the quadratic formula are exactly the solutions that are needed to be able to write the general solution to the equation number 1. Okay, now we won't tell you how to solve this whole business because this is really the domain of Math 2A. But when you take your characteristic equation and you solve for lambda, that's the unknown, use the quadratic formula, you get two solutions, or one solution if the square root happens to be 0. In which case lambda 1 and lambda 2 are equal to each other. Here's the solutions via the quadratic formula, lambda 1 and lambda 2 being our solutions. And it's the nature of these solutions that drives the form of the solution to that differential equation number 1. So in case 1, if lambda 1 and lambda 2 are real numbers, with lambda 1 not equal to lambda 2, and this will always be the case as long as b squared minus 4ac is positive, then the general solution has this general form. You can verify that this satisfies differential equation 1 for fun if you want. Some constant c1 times e to the lambda 1 t, lambda 1 was one of the solutions to the characteristic equation, plus c2 e to the lambda 2 times t, where lambda 2 is some other solution to the characteristic equation. In case 2, in the case that this occurs when b squared minus 4ac is equal to 0, in which case you have a repeated root, so lambda 1 and lambda 2 are just equal to some lambda. Lambda would be minus b over 2a. The solution here is given by x of t, c1 e to the lambda 2t plus c2 t times e to the lambda t. This is the general form of the solution in that case. In the third case, if lambda 1 and lambda 2 happen to be complex non-real solutions, this occurs when b squared minus 4ac would be less than 0, so this is a possibility here. This is the most complicated form of the general solution. You get e to the lambda t times the quantity c1 cosine of beta t plus c2 sine of beta t. And just because the notation in 3 lambda plus or minus I times beta, I just wanted to explain how this works. So suppose when I solve for lambda 1 and lambda 2, I'll just make up some solutions so you can just see how this would work. Suppose I get, I don't know, minus 1 plus or minus the square root of minus 4 over, I don't know, 5. Okay? So what I have here is, if I just simplify this, this would be negative 1/5 plus or minus. Now the square root of negative 4 is 2i, so I'd have plus or minus 2/5 I. So the thing that we're calling in this notation alpha would be negative 1/5. And the thing that we're calling beta is what's the positive. It's a real number multiple of I. So beta would be 2/5. And so your general solution down here would have this general form. X of t would equal e to the negative 1/5 t times the quantity C1. Whoa. Sorry about that. Sometimes my pen goes crazy on the drawing tablet here. C1 cosine of beta, so that would be 2/5 t, plus C2 sine of beta t, sine of 2/5 t. So that's how this general solution, what this would look like in my made-up example, just so you had an idea of what we're talking about when we refer to alpha and beta there. So that would be the example. Okay, e to the alpha t, C1 cosine of beta, cosine of 2/5 t, plus C2 sine of beta, 2/5 t. So that's how you find the solution x of t. So now let me go back. Couple pages here. Okay, so the first thing I'm going to do is put this in this generic form, 1 times x double prime of t, putting this in the form of equation 1 on page 15, plus 0 times x prime of t, minus 2 times x of t equals 0. And then directly below that, you form your characteristic equation. 1, the x double prime becomes lambda squared, plus 0, the x double prime, the x prime becomes lambda to the first if you like, minus 2, and then the 2 just becomes the constant. 2 times x of t just becomes 2 in the characteristic equation. And so, more simply, what I really have here is lambda squared minus 2 equals 0, and that of course implies that writing the solutions as lambda 1, lambda 2, the two solutions, I get lambda 1, lambda 2 are equal to plus or minus the square root of 2. And just to be as clear as possible here, you can let lambda 1 be either of these. I'll just let lambda 1 be the square root of 2 and lambda 2 be the negative square root of 2. And so x of t then, following the solution that's given on page 16 of the survival guide, you have C1 e to the lambda 1t, so that's square root of 2 times t, plus C2. These C1 and C2 are arbitrary constants. You have to find these. Well, I'll show you how to find these in a moment. Minus e to the square root of 2 times t, that's lambda 2. Now to determine C1 and C2, also I need to solve for y, so let me just go back a page. Remember, y of t was x prime minus x of t. I know what x is, so I can find x prime of t. So to find y, I use that solution, just solving equation 1 for y of t. In terms of x and x prime, I can get y, so let me write that. So y prime of t is equal to x prime of t minus x of t. And remember, you've got x of t here, so when you do this, you're going to get, well, x prime is equal to, what is that? That's c1 square root of 2 e to the square root of 2 times t. I'm taking x prime, and so then that's going to be minus c2 square root of 2 e to the minus square root of 2 times t. That's x prime minus x of t, and that's c1 e to the square root of 2 times t plus c2 e to the minus square root of 2 times t, x prime minus x. And if we simplify this, so what are we going to get here? Well, you got to do a little algebra. So what happens? We have c1 times the square root of 2 e to the square root of, so if you combine this c1 here with this c1 here, we get c1 times the square root of 2 minus 1 e to the square root of 2 times t. And then you can see that the let's see here, let me go back a page. Y of t was x prime minus x. I've got a prime here that doesn't belong there. Just fix this. So let's see here. So that's c1, and then y, the second component here of y. So I've got a negative c2 times the square root of 2, and then I'll have a negative c2. So I'm just going to write this as minus, I'm going to factor that negative sign forward since I have two negatives, and then I'll just write this as the square root of 2 plus 1 e to the minus square root of 2 times t. So that's y of t. So there's your general solution. You've got x of t, y of t, and from those you can find r of t. And so the last part of the problem is to actually use the initial conditions to determine what c1 and c2 are. So that's going to come from this right here. I've got x of 0 is equal to 1, y of 0 is equal to the square root of 2 minus 1. So I'll have to do that on the next page. Bring that page up here. So okay, so looking at your function for x of t, setting x of 0 equal to 1, and then substituting, what you're going to get here is x of 0 will just be c1 plus c2, and that's going to have to equal 1. Go back a page so you can see that if you plug in 0 for x in this equation right here, you're going to get e to the 0 and e to the 0, so you just get c1 plus c2. And when you evaluate y of 0, you're going to get c1 times the square root of 2 minus 1 minus c2 times the square root of 2 plus 1. So that's what you get for y of 0. And y of 0 has to equal the square root of 2 minus 1. So let's just write all that down. Y of 0 equals the square root of 2 minus 1. So that's going to imply that c1 times the square root of 2 minus 1 minus c2 times the square root of 2 plus 1 is equal to the square root of 2 minus 1. And if you look real hard here, these are the same expressions. So this suggests that you should put c1 equal to 1 and c2 equal to 0. And you can check that that solves the system of equations. And so therefore my particular solution is x of t. So substituting c1 and c2 now into my solution for x of t, I get just e, or 1, times e to the square root of t. In y of t, this is the particular solution to my differential equation. I get the square root of 2 minus 1 e to the square root of t. And again, all I'm doing is just substituting 1 for c1 and 0 for c2. So if you go back, in y of t, if you substitute 1 here and 0 here, you just get 1 times the square root of 2 minus 1, so just the square root of 2 minus 1 times e to the square root of t. And if you substitute 1 for c1 and 0 for c2 in the equation for x, you get e to the square root of 2 times t. So that's where those are coming from. And you can even eliminate the parameter, since I've got the same expression here and here, and this guy is just equal to x. I can also write this without the parameter t as y equals the square root of 2 minus 1 times x. So you can see that this flow line is a linear function. And in fact, that's what we have right here. So if I put an orientation on my path up here, that guy there is my initial condition. So that's where x is equal to 1 and y is the square root of 2 minus 1. So that's the starting point. And then this line is y is equal to the square root of 2 minus 1 times x. So there's your flow line in that case. Okay, let me just move on here. So as a sort of fun challenge problem, we've got the general solution. Part B gives you the general solution here. So we just did that. We finished part C for the linear flow line, but you can see in this vector field that there's different flows here. Not all the flows are linear. So for fun, we started up here in part D, and this is one you should do on your own. Suppose that the initial position is x of 0, y of 0 is equal to 0, 4, so that corresponds to the point 0, 4. And you can see this flow line is going to move in this direction, obeying the vector field. So imagine these vectors are river flow. And my little boat's going to flow along this curve. And so the question is, what's this flow? So what's r of t going to be in this case? So you're going to have to go back to the general solution in B. You've got your initial conditions. X of 0 is going to have to equal 0. Y of 0 is going to have to equal 4 here. So you're going to have to solve a little system of equations involving C1 and C2 after you substitute. And after you're all done and you've simplified, you can check your answer to D. And for even more fun, you can graph this on your graphing calculator. So you can enter this in the graphing calculator, and what you should get looks exactly like this curve that we've drawn in the picture for you. We graphed all this in Mathematica, but you can also actually plot the flow line using your graphing calculator, using the parametric function mode. So that's one you should try on your own and see if you can get that yourself. So do part D on your own, and next week maybe I'll have something else for you to do with this. I'll cook up with something for you to do for practice here, so you can try something similar to this on your own. So anyway, that's it. That finishes 17.4, and this completes our discussion of